Hi, I'm Dan Polis. I'm from NASA's Goddard Space Flight Center, and I was the materials and process lead on the composite crew module. At the Goddard Space Flight Center, we typically deal with unmanned missions, and composites play a big role in that in terms of metering structures for space telescopes because of their stability with temperature and extreme temperature environments. The composite crew module was really an exciting, unique challenge for us in that it's really the first time that NASA's looking at a habitable module, a manned environment made out of composite, and really going after it because of composite's unique strength for its weight or its specific stiffness, as well as its specific strength. Really in the design phase, trading different concepts, one of the most unique things about the crew module and composites is their ability to form complex shapes relatively easily. And if you look at the shape of the crew module, we have this lobed design floor, which really led to a significant weight savings by allowing the shape of the dome to be pre-deformed. From a materials perspective, it presented a unique challenge, and that's to have that lobed floor and attach the backbone. We have these 90-degree joints, which in composites is a challenge, and we brought some new technology that's been developed recently using woven carbon fiber preforms. And so that was one of the main aspects of the design where materials got involved, both bringing that new technology, going into the lab and testing that technology to make sure it could meet the required design constraints from a strength perspective. And then moving into the manufacturing phase, how would you scale that technology up? And so a lot of this was developed in the Department of Defense, private sector, and NASA brought that in, brought team members from those different areas that had already had experience, and then applied it to this unique concept. We also play a big role, the materials team, in defining what's called design allowables. So again, what capability can you design a material to? How much tension or compression can you put on a material? And we feed that into the design team so they know how thick the walls need to be. From a processing perspective, unlike metallic vehicles, you buy a sheet of material or a billet of metal, the properties don't change as you machine it. Composites are unique in that the manufacturing and the properties are tied. So when you move from the design phase, where we give performance properties to the design team, we have to make sure that when we move into the manufacturing phase, we can achieve those properties. So the materials and process team help develop the processes to build these large shell structures made out of carbon fiber face sheets and aluminum honeycomb core. And we work both testing in the lab, building coupons, and then scaling up to larger scale fabrication to show that we could meet the capabilities that we designed to. We also interface with other parts of the design, the non-destructive evaluation team, to define critical areas that need to be inspected. So knowing different failure modes, for instance, if I come back to this attachment of the backbone beam to the shell, the critical way it fails, we observe in the lab, and we know those are the critical areas that have to be inspected, and we apply that for the non-destructive evaluation team. So that's kind of integrating the design, manufacturing, non-destructive evaluation. As we move in through the test phase of the program, the materials team is constantly evaluating critical areas, both visually through non-destructive evaluation and helping to look at what capability we expect to be able to test to. We've also, for composites, one of the things that is of most interest is its ability to perform after impact. For metals, if you impact metallic components, their performance doesn't really change with damage. Composites, you do see a drop in performance, and so we're showing at a full-scale level on composite crew module that this shell is robust to the kind of damage you'd see when integrating it with oxygen tanks or any other electronics to build this up into a vehicle that would fly with humans. So it has to be tolerant if you bump it to know that its performance hasn't dropped. And so we're demonstrating that at the full-scale level. Composites have played a huge role in NASA spacecraft at the Goddard Space Flight Center for many years. And the reason being is they have a very unique property in that they don't expand or contract. And you can imagine a spacecraft going around the Earth and getting hot and cold while it's a camera trying to look at a distant object. If that were made on a metal spacecraft that would be expanding and contracting, the camera would be vibrating or the optics would be vibrating. And so that's one really unique area that has already seen major success in the space industry. Applying composites to manned vehicles has some additional challenges. Of course, mass is critical for spacecraft. Every pound of space is very costly. And composites have incredible specific stiffness. So you apply a certain load and how much do they bend. They don't bend very much for their weight in comparison to metals. And they're also very strong. So they can handle a lot of load or stress before they break. And you see this aspect in their usage in commercial industry like bicycle frames, tennis rackets. Again, for their specific stiffness on a tennis racket, you hit it, all the energy is returned to the ball, there's not a lot of deflection of the racket, and it's lightweight so you can swing it over and over again. The materials we use typically start out as the highest grade materials, the fibers that are the strongest or the stiffest, and then eventually more volume is created that can go into the private sector and costs can come down, and that's happened in a number of cases. We have also some really unique applications that are used where fibers have very low thermal conductivity. And we use that where I always equate it to the McDLT, the hot side hot and the cold side cold. You want a cold part of the telescope to view distant objects, but the electronics have to be hot. And you can put composites in between those two so there's no heat transfer from one side of a spacecraft to another. With metals, that's difficult to do. The materials discipline really spans a pretty large range from looking at what materials fit a given application, off-the-shelf materials that have either been used at NASA or used in the private sector. And for the composite crew module, we used a lot of technology that already existed. Materials to make the skins and core are very common materials, but our focus in the materials discipline would be to apply them in the right instance to make sure that we have robustness of a structure. There's also a lot of work that goes on to develop new materials. Where there's weaknesses, for instance, in composites is their ability to take load through the thickness. And so resin chemists work on toughening those materials, making those stronger. For spacecraft, that may be adding particles so they can conduct electricity when they're in space and dissipate charge. So there's both fabricating new materials for space, improving on existing ones, and then unique applications where technology that's used in the food packing industry could be applied in a unique way inside the pressure vessel. And that case is to contain leakage of a vessel, to use something as simple as packaging of food materials applied directly to the composite. The tools we use is anywhere from a tensile testing machine pulling on coupons to get their strength and specific stiffness, to some pretty high-tech imaging methods to get full field strain of a complex article, to look at failure modes where things start to break apart. Other techniques, a lot of times we'll do chemical analysis to figure out whether a process has developed like we expect. Like the cure of a composite resin, you can evaluate it chemically to see how far it's progressed. And that's often important to make sure that you control processes at the coupon and full scale level. I guess I never knew I wanted to be a materials scientist or engineer until I had an internship at a company near Philadelphia and was working on, or asked to work on, a project to create complex ceramic forms in a polymer. Essentially, you've seen many plastic parts. Well, we used that technology to be able to mold plastics, but we filled it with a ceramic powder. And I was amazed that you could just make a part that looked like a plastic, heat it up to 1800 degrees Celsius, and end up with a ceramic part that could withstand temperatures of 1200 Celsius and be as clear as glass. And it just opened up my eyes to the possibilities of what could be done with materials in unique ways. And at NASA, it's been a dream come true to be able to take that and work with composites, pretty simple carbon fiber and, again, plastic matrix, and be able to build spacecraft.